Welcome, everyone. My name is Natan Silnitsky, and I'm a backend infrastructure developer at Wix.com. And this talk is about the key decisions that we have made at Wix over the years on how to scale Kafka, our Kafka-based distributed system, to more than 1,000 Scala microservices. And I want to share with you the best practices, tools, and SDKs that we have created in order to achieve this. But first, we're going to start off with a very quick Kafka introduction for those of you who are less familiar with it. So what is Kafka? Kafka is a message broker that allows to work with the publish-subscribe model and also allows for much greater fault tolerance for our distributed system. And here we have the Kafka producer that will produce a message over to a topic. And this topic is divided into specific partitions. And each partition is a append-only log. So that means that when the producer will produce the message, it will be put at the end of the log. And that will be part of the broker spinning up in memory, or if it's cold, it will be in the disk. Now, we have over here the Kafka consumers. So these are, both of them read from this partition without any regard to one another. And they scan it sequentially, and they do it in their own pace. And unlike with message queues, they don't remove the message once they finish processing it. They just commit it. They specify that it's committed. And then if there's some restart or some error, they will just start off after partitions are redistributed from the last committed message. And because of this sequential scan property, it's a very fast performance and great for scaling as well, because all you need to do in order to increase your level of parallelism and scale is just increase the amount of partitions. So it's really that easy. And yeah, that was a very quick Kafka introduction. Now let's talk a little bit about our Wix setup. So we have around 180 million registered users that are really use our Wix even now more than ever with the Corona situation. And about 5% of all internet websites run on Wix. We have around 3,000 people working at Wix, around half are R&D. And we handle around 500 billion HTTP requests per day and serve 6 petabytes of static content. Now, we don't use Kafka to serve the static content, but we do use it a lot. So you can see here that we've already arrived to more than 1 billion messages produced every single day using Kafka. And it's not the only scaling axis that we have grown a lot in. We also have a lot more microservices now, mostly in Scala, but there are also some in Node.js. And backend developers amount has really grown. And not only backend developers use Kafka, a lot of front-end developers use it in their Node.js services middleware. So there are a lot of scaling concerns in different criteria, not only traffic. So how do we handle it when we have both traffic increasing, but also all the amount of metadata, developers, use cases? How do we handle that? So I want to share with you the key lessons that we learned. And we'll start off with lesson number 1 about common infrastructure. And this relates to the fact that we have a lot of developers working and they have a lot of use cases, and we want them to work and develop fast and not think about the Kafka boilerplate, and support them with the features that they request. So the first thing we do is we have the Greyhound library that we have developed at Wix, which basically wraps the Kafka SDK client. It wraps both the producer and the consumer. And this really helps us with simplifying the API for our developers, and also add a lot of features on top of it. We reduce a lot of the boilerplate that the Kafka API has. And also it offers a level of abstraction where we can do a change behind the scenes and everyone can get it immediately when they GA. So it's really beneficial. Now, recently we rewrote the Greyhound library with the Zio. So of course, this is a Scala conference, so a lot of you know that Zio is a functional library, functional programming library for Scala that's great for concurrent asynchronous programming. So it's really beneficial to use for the Greyhound use case and Kafka use case. But of course, not all Wix has written the code in Zio yet. So we also offer feature-based APIs, a layer on top for our developers. Now, let's look at a few of the features that we offer. So the first thing I want to focus on is the simpler consumer API. And here we have the Kafka consumer that when you create it, you have to specify all kinds of things. The most important ones are the broker locations, of course, the addresses, and also what type of serializer, deserializers you use for your key and your value. For this consumer, for instance, it uses the sum message type as a value. And a lot of other properties you usually set up. Now, when you want to start consuming, with Scala, you can do a recursive function. And you first start off with polling the consumer, and then you'll get the records. And now you do some for each operation on these records, and you do some side effect here. And now you have the commit that I talked about on the introduction, where you want to specify to the Kafka broker that you finish processing these messages. You can do this automatically with Kafka, set up auto commit, but then you may end up losing messages and not processing them. So it's best practice to explicitly specify the commit with the Kafka. And then, of course, we have the recursion doing it again and again in endless loop style. So you can see that quite a lot of boilerplate here. Let's look at how we do this with Greyhound. So we specify the record handler. It uses, from the Zio environment dependency, it uses the console, the specific handler. It doesn't have any errors emitted. You see the error channel is nothing. And it, again, uses the string and sum message for serialization of specific topics. And we just specify the lambda that we provide for the record handler. And we provide this handler to the consumer builder. So you can see here that there is no explicit commit done. The Greyhound will take care of it for you once the handling is completed. It will commit the messages. And you also don't need to specify the broker location because Greyhound, behind the scenes in the configuration file, will inject the production broker address. Great, so that was the simple consumer API that Greyhound offers for our developers. Now let's talk about parallel consumption. So if you look at the Kafka consumer, you can see that it really doesn't hint at any multi-threading. So the consumer poll has to be done on a single thread. And if you want to increase the level of parallelism, one option is to create multiple Kafka consumers. That will be less resource efficient. Another option is to take these messages and do some parallel processing with them and make sure that you commit all of them and handle errors, etc. So there's quite a lot of boilerplate done here for parallel processing. And sometimes it could be difficult to do multi-threading, etc. So with Greyhound, we decided to use CO fibers, of course. Zio fibers are basically lightweight threads. You can think about them like that. So they have less resource usage than the Java threads. And it's much more efficient. And we also use Zio queues in such a way that each partition that is assigned for our specific application instance will handle messages on a specific Zio queues on a different fiber. So basically, we have the utmost parallelism level that we can in this setup on our instance. And of course, we can limit the amount of parallelism easily if we want. But you can see here that using Zio, it really makes it straightforward and really easy to have the parallel work done in a really few lines of code. So it's a really beneficial rewrite that we did, because before that we used all of the Java synchronization primitives and all of the atomic references and specific Java threads, which are really less resource efficient. So we're really glad about this rewrite. Okay, so what about error handling that I already mentioned? We want to have fault tolerance. So Greyhound offers the ability to do retries. You just specify the retry policy, and then you will see that here that the retry policy means that if there is a failure, we want to retry after 1 second. And if that doesn't succeed, we will retry again after 10 minutes. So, and then we just specify the retry policy in our builder. So very fluent and simple API. And behind the scenes, what will happen? So let's say that we have some subscription renewal topic that we consume messages from. And then if the processing fails for some reason, we will have a built-in retry producer inside the consumer that will produce the message to a retry topic. So we have retry 0 topic for our first interval that we set for 1 second, and the second retry topic after 10 minutes. And this design was inspired by Uber. You can check out the link here that I'll share with the slides. But there is an issue here. Retry topic will cause your cluster to grow faster. Why is that? Because you add more partitions and more topics, right? For each single topic, depending on the amount of retry intervals that you will set up, you'll have many more topics, retry topics, and many more partitions. So that means your cluster will start growing in a faster pace than if you did not have retry topics. So that can cause potentially bigger load on your cluster. So one way to mitigate this is to offer only a single partition, can set up only a single partition per retry topic. And usually we can say that errors happen only rarely, and the performance of error handling will still be quite nice, even with one partition. And of course, if we notice that there are a lot of error patterns in our application, we can increase the amount. So there's a trade-off here with the amount of partitions for the retry topics. And there are other ways to handle the retry situation with Kafka. I won't go into too much detail, but there's no silver bullet in a perfect design with Kafka for retries. Each one of them will have their advantages and disadvantages. Now, you may have noticed that we are doing out-of-order processing with this retry design, because once we put the message that we're currently processing, message 5, into retry topic 0, we can then continue processing messages on our original topic with message 6. So, and we may end up committing it. So we do processing out of order. So if you have a situation where you have to have order processing, for instance, you have a topic that scans the latest GitHub commits. So you want to handle them in order, but you do want to handle errors. So for that, we set up a blocking policy in Greyhound where it will just simply keep retrying the same message on failure again and again. Now, while this guarantees order, it may introduce a lag between the producer that keeps producing messages over to these partitions and the consumer that is stuck on a single message. So for that, we have a dashboard that is automatically created for each of our applications, and the developer can check it out and view the message that is currently blocked, view its content, and decide whether they want to unblock this specific message because the doesn't look interesting and the error is not interesting. Or maybe they decide that this is a bug and they're going to fix it. So all I have to do is fix the bug, redeploy their service, and then hopefully there will be no blocking and the lag will go away. And they fix the situation. So they can really monitor things in production really easily. Okay, cool. Another important thing I want to mention about Greyhound, which is very important for us at Wix, is its ability to do context propagation. What do I mean by that? So we have a situation with a browser and a user, a site visitor for one of our Wix sites that wants to sign up and be a member of the site. So when they send out the HTTP request, it of course has all kinds of important headers like language and geography, and also Wix-specific headers like the user type. Is it a visitor? Is it a registered users? So all this information goes into the site member service request. And when the site member service will produce the message in order to allow others to consume it, the sign-up request, then Greyhound will automatically put all of these headers into the Kafka message. And then we have other services that consume this message, like the contact service that manages all of the Wix site owner contacts, will be able to automatically, through Greyhound, get all of this user request data and then persist it to database if they want. But they get it out of the box. Okay, great. So we discussed a few Greyhound features. We're going to come back to Greyhound a little bit later. But now I want to switch gears and talk about self-service. So we have a lot of developers and use cases, and only a small team that is working on the Kafka infrastructure. So it's really important to give our developers all the tooling and documentation for them to help themselves and not have our team as a bottleneck. So here you can see that we did get a lot of questions on our Slack channels. We still get a few questions now and then, but a lot less than before. For instance, how do I search for Kafka messages? Or how do I increase the number of partitions? So we decided that tooling will be very helpful in this situation. And while there is the Kafka CLI scripts, like consumer groups and console consumer, but it does introduce a learning curve to know them, all kinds of flags that you need to use. And developers need to use this only once in a while, and they like scratch their heads and how do I use this? So it's the standard, but it's not the optimal tool, in my opinion. We also have the Yahoo Kafka Manager in the industry, which is open source, which is great. And there's also Confluent Control Center, which is a commercial product. But we decided to create our own control plane for Kafka that will handle our custom needs. So here you can see our control plane. We called it the Greyhound admin. And we have the topic configuration screen. So here our developers can view the configuration for each of our main DCs. And then they can also change the configuration. Most importantly, they can increase the amount of partitions, which I described before, to scale up. And yeah, that's pretty much what you can think about for the configuration. Another screen I want to share is the live topic stream. Here, the developer can choose a topic, choose a data center, and then choose from which time they want to start getting messages streamed. They can also filter according to key or message or header. Then they get the messages starting to show on the screen. When they click on a certain message, they see metadata telemetry on it. For instance, which artifact produced the message, and which services artifacts at Wix have consumed the message at which times. If they scroll down, they can see the actual payload of the message in nice JSON format, and they can copy-paste parts of it or the entirety of it. And if they scroll down further, they can see all of the headers that were part of this message and help them with investigation, etc. So that's very helpful for them. And we also have a key value store screen for our Greyhound admin control plane. You may ask, what are key value stores to do with Kafka? So Kafka has the ability to act as storage. It has the concept of compacted topics. I don't want to get into too many details as it's out of scope for this talk, but basically you can load all of a topic into a local file database or in memory if it fits, and then you can use it really, really efficiently as a key value store where the values, only the latest values are kept by Kafka. So this screen allows our developers to view what kind of records are currently found in the key value stores for their configuration, dynamic configurations in their application. That's very helpful for them. So here they also choose the topic and filter by key value and choose data center, and then they can view the keys and the values and also get live updates on them. Okay, so that was about our tooling. Now let's talk about documentation. Sometimes our developers need to investigate what's causing a lag between producer and consumer, right? And they also want to have helpful information on Greyhound, let's say how to add retries on errors. So we have a few kinds of documentation available. First, we have the GitHub README that stores all the information for our Greyhound APIs. Then there's also our internal Stack Overflow question and answer style, which is very helpful for people asking questions. And we also use a custom developed Slack bot that answers questions without actually needing the developers of the infrastructure team needing to be present. So here you can see an example of the Greyhound README, small part of it. And you can see an example of our internal Q&A on how to investigate Kafka consumer lag. So a lot of people view it as a quite popular question and answer. And you can see here on the bottom of the screen, we have our ChewBot, where it can answer the questions that our developers have on the Greyhound Slack channel and possibly help them get their answer immediately, which is very, very cool. Okay, and another aspect of documentation is, of course, how a developer can discover topics and message structures of our services that they require to consume. So we have all of the messages defined structure in protobuf, and then it is able to be exposed by our internal API site that is automatically provided with all of these protobuf files. And then it is posted on the site in this format that you can see on the right-hand side. So you can also not only see the Kafka messages of the service, you can also see the gRPC requests. And because we use gRPC at Wix, it's the main reason why we chose protobuf. So you can see REST endpoints, gRPC endpoints, Kafka events, and all the details on them. Now, on the industry level, we also have Avro, that is there's another formatting like protobuf that's quite popular as well. And Confluent offers the schema registry that utilizes Avro and allows developers, again, to discover topics and message structure. And it also manages the version history of the schemas that are used by the Kafka producers, etc. So that's also quite helpful. And that's also widely used in the industry. Okay, so we talked about self-service. Lesson number 4 is about testing. So we have a huge amount of microservices, huge amount of code and use cases, and we don't use any QA engineers to test our code, our backend code. We use TDD, test-driven development mostly, in order to make sure our services have high quality. So testing needs to be simple, straightforward, and easy to do. That's why Greyhound offers a test kit for our developers, and it spins up an embedded Kafka broker and Zookeeper, and then it will inject the local ports of the broker and Zookeeper automatically to the test environment of our developers, and then they can run tests against it. And the test kit also offers a message sync that allows the developers to check that they produce messages in a correct manner. Excuse me. So this really improves the development velocity of testing as well. So it's really important for Wix, not only production code, but testing code, having development fast and accurate. Cool. So the 5th lesson I want to discuss is monitoring. So we have a distributed system that is completely async and event-driven with Kafka. And monitoring this is really not that straightforward. The most important thing we do in order to mitigate this is that Greyhound automatically offers all kinds of custom matrix through the producer and the consumer to be consumed by our matrix server that's Prometheus in our case. And there are all kinds of custom matrix, like what's the historical handling time of each message for the topic and consumer group, or what's the current highest, longest running handler. Maybe it's stuck, so we want to know about it right away. And about information about lagging, and of course, the produce rate and consume rate and exceptions, etc. All of this is provided automatically in our Grafana dashboards for each service, and our developers can go there and see all the information needed for their artifacts when they debug some issue in production. They will also get automatic alerts from the Grafana setup, both to their Slack channel that they automatically designate for their team, and of course for all the emails, addresses of the team. And it will also, the alert will also go to the on-call application, on-call developer, the application that handles all the on-call alerts as well. Cool. So this gives us a lot of visibility for our developers in production. And here you can see an example of an alert that our developer received, the slow consumer handler execution alert. So they need to investigate why is their code running a handler that's taking so much time, a lot of minutes, and causing the lag to evolve. And you can see our developers are very responsive, and they acknowledge this alert in less than a minute. Cool. So we are good for our developers in both how they write their code, how they set up their topics and partitions, how they debug production, how they view what's going on in production, and how they easily test. That's good. Now let's look over on the cluster situation. It's really important to have a proactive broker maintenance approach. this is a very important piece of information for you to know when you use Kafka. Currently, with the current version of Kafka, a broker should have only up to 4,000 partitions handling, and the cluster itself should have optimally no more than 200,000 partitions. So this is really important for a healthy broker and cluster to be maintained. As if you put more and more partitions on the brokers and clusters, you have slower performance, especially when some broker goes down and up. It will take them a lot more time to get all of its partitions back. So add more brokers when you see the need for that, and split clusters to smaller clusters when the need arises. And also delete unused topics. Sometimes topics are already unused and you can just delete them safely. So that can also help the situation. So we want to avoid hard failures. We want to avoid slow performance. The idea is to have active maintenance. And the good news is that should happen this year that the Confluent, the company behind Kafka, is going to remove the Zookeeper dependency of Kafka. And they claim that this will really remove the bottleneck from the amount of partitions that the cluster can have to a lot more, like 1 million partitions. So that will be very helpful. So stay tuned for Kafka detaching itself from Zookeeper. Okay, lesson number 7 about cross-DC producing. If you have a situation that your system is globally deployed, like with Wix, I think it's very important to try to avoid active auto produce. What do I mean by that? So let's say we have 2 data centers, DC1 and DC2. And we have requests coming in from a browser to update the user's site. So the service handles it and produces the message over to Kafka, message number 1. Then the user on the browser sends an additional update request. And this time, because we have an active deployment for our DCs, it ended up going to the service on the second data center. And it's produced to Kafka, and now Kafka has update number 2. And of course, we want both data centers to have the complete picture. So we use replication between our data centers in this situation. But now you can see that DC2 is inconsistent with DC1, and the messages on Kafka Broker are out of order. So for some use cases where you need ordering in your Kafka consumers, this is a really bad situation. So the simplest way to mitigate this is to only use the service that produces the messages to be handled only on one data center, to have a sticky in one data center, and they do like active passive for the write side, for the produce side. And what happens here is that now we have a consistent view of the Kafka broker partition. Message 1 is followed by message 2. And when we replicate it, it will be again consistent on the second data center. Of course, and then all the consumers on both data centers are free to consume it as they wish, and they don't have to be active passive. They can also be active if that it doesn't hurt them. So I'm only talking about the produce flow. But of course, there's the downside here is that the request may take longer to get from certain locations in the world to the service that is producing, and it'll be less fault tolerant because it's farther away. Everything here is a trade-off. You can do other kinds of implementations to handle active produce writes, but this is by far the simplest, most effective one. Okay, lesson number 8. That's a lesson for our systems that have polyglot in them, specifically Node.js or Python, it's really helpful to avoid using the Kafka SDK directly in Node.js. So at Wix, we used to use Kafka directly both in Scala through Greyhound and in Node.js for a different library that produce and consume directly from the Node.js application. Now, it's really not optimal to do that with Node.js. We have the single event loop, and it works much better with the JVM applications. And also, we want to have our developers use a lot of common infrastructure and a lot of cool features. And it's really bothersome to keep replicating these features and bug fixes between Scala and Node.js. So our solution was to introduce a sidecar that for each Node.js, meaning that when the Node application pod spin up, it has both the Node application container and a Scala service container that is basically the proxy for Kafka that just creates a Greyhound consumer and producer according to the Node application specification. And then when the Greyhound sidecar will consume messages, it will then send a gRPC request back to the Node.js application that can handle these requests much better. And this approach really helped us get the features much faster, both to our Node.js developers. But the downside here is that the memory footprint does increase when you use an additional container for each of the pods. That obviously means a lot more memory usage. We could have chosen to put Greyhound in the daemon set or the Kubernetes node, but then it will be a much more complex architecture. So we decided to simplify it and stay with the current memory footprint, just optimize it for the sidecar. There are other usages, alternative usages in the industry. There's the Confluent REST proxy that solves the exact same situation. A lot of companies do their own proxies. It's quite a common pattern with Kafka. Nice. So the 9th lesson I want to discuss is consume and project. Okay, interesting. What does that mean? So we have a situation where our services have a lot of throughput. For instance, our meta-site service that has a very popular flow to fetch information regarding sites, Wix sites, like what is the site version? Who is the site owner? Or what applications are installed on the sites? Is there a store or a restaurant application installed on the site? So all of this made the meta-site service a bottleneck on its database, and it serves 1 million RPM requests. And there's a load on the database here because there's a large meta-site object that every time needs to be read and write for these queries and updates. So what the team behind Metasite decided to do is they wanted to split up the popular site installed apps request away from Metasite service. So how do they do that? So first, they produced all of the site updates to the Kafka broker in order to Kafka to have all the information from the database and any updating going to the database about the site being updated. Then they created an additional microservice that is just in charge of the installed apps context, and they utilize the consumer then of the service will just filter from the site updated messages that include the entire context, only the site installed apps part. So that's the projection part. We only project part of the information that we are interested in our consumer. And then we put it on its own database with only the installed apps context of the meta site. So while there's duplication of data here, it makes it much easier to handle the growing performance and load in an eventually consistent manner. And another additional optimization here is to split up the write service from the read service. So all the gRPC requests that are interested in installed apps metadata for the site will go to the reader service. That means that the load on the writer server keeps being low, and it can be very close to the meta-site service data center inside the same data center. But the reader service can be put in any data center or point of presence around the world easily, because they will just read from replications of the database that will be put, that are set up also across the world. So you can have different SLAs for write and read, very simply this kind of design where you split read from write. But this, but this was powered by the ability to utilize Kafka and have the monolith provide the big object, and the new microservice only limit the scope by consuming and projecting part of it. Okay, we're coming up for the 10th and last lesson of today, and it's about event-driven end-to-end. So Kafka messaging is event-driven, of course, but is it only relevant for service-to-service communication? How about browser-to-service interaction? The user is waiting there for a response, so event-driven doesn't seem really relevant there. Maybe? I don't think so. We can use WebSockets together with Kafka to have a complete event-driven solution that works really well for a lot of use cases. Kafka and WebSockets can work really well together. So let's look at the use case. We're running a context importing task where the Wix site owner wants to import contacts from other locations, maybe their Gmail account. And this is a long-running async business process, right? Because there are a few services that are involved. We have the contacts job service that produces these jobs requests and puts them to Kafka. We have the contacts import service that actually will handle these job requests one by one in its consumer. And we have the WebSocket service that will be able to help us with our browser interactions. So the first thing we need to do is to subscribe to notifications from the WebSocket service. Then the browser will request to import contacts, maybe from a CSV file that was previously uploaded. So the job or multiple jobs will be created by producing them to Kafka. And then the context import will be able to consume these jobs. And once it's done, it's able to notify the WebSocket service, which then will notify the browser. So now the user can follow up on what's going on with the import process. We can send it intermediate notifications, like a progress bar, and keep updating about the progress. And all of this done completely asynchronously. There could be a lot more services involved in this, and the user will not know about it, and everything will happen asynchronously in a completely distributed manner. Cool, so to summarize, what do you do when the traffic, metadata, and amount of developers and use cases keeps growing? Wix has created an entire ecosystem to support large-scale Kafka-related needs. And I'm glad to announce that Greyhound is also open in alpha, so you can go and check it out. We're doing a few last improvements for our Greyhound code, so hopefully it will be very soon open officially for beta users, for you to use in your own code and organization. So thank you very much. If you want to get updates about Greyhound and about other topics that I write about on Kafka-related and event-driven related information, you can follow me on Medium and Twitter to get updates. The slides I uploaded to SlideShare. And Lech, that's all from me. I guess we can maybe start with the questions, right?
Yeah, fortunately, I have seen 3 of them, so I don't have to choose any, and we still have a few minutes. So the first one was about the test kit, and the question is, does it also work with Java or just with Scala test libraries?
Okay, that's a good question. So on the open sourcing that we're doing for Greyhound, we offer a Zio layer and not only a futures API layer on top of it, but also a Java API layer as well. So the test kit, I'm not sure if you already implemented the Java API for test kit, but it's definitely part of the plan, because the idea is that Java developers can utilize the Greyhound on all aspects and all features.
Okay, thank you. This second question is about, again, about integration this time. Is it possible to integrate Greyhound with other effect types than Zio?
Right, so like I mentioned in the previous answer, we have Greyhound is designed in a layered structure where the most basic one is Zio. So the setup for future-based APIs and for Java API is simpler than currently it is with Zio, because it's more low level currently with Zio. But you may have a little bit more integration to do, but you can definitely use it and integrate it with the CATS effect and stuff like that, because Zio offers these kinds of interoperability. And we also want to have the integration layer on top, also more streamlined for Zio, like an opinionated Zio level on top of the more low-level Zio. So
okay, I understand. Yeah, thank you. And the last one is a little bit longer. Let me just read it. Great talk. Can you say something about the sweet spot of centralization? You presented many examples of how common tools help you to retain high velocity with a growing team and feature set. However, I could also think of cases where forcing teams to match into a common toolset slows you down as the common toolset grows in complexity and cannot keep up with all requirements of your team.
Yeah, that's a great question. So I'm currently in a team that writes infrastructure code. And the biggest challenge here is really not to keep it simple, keep the APIs as simple as possible, and especially and hide the unwarranted complexity away from our users. By the way, Zio also really simplifies this greatly, the infrastructure code, so really pleased about that. And my philosophy in general is that if you have to write something that's more on the framework level and not on the library level, you still want to have the framework just be an integration layer on top of the library's API. So it kind of connects to how I answered all of the questions today, that you want a modular design that offers low-level libraries and high-level integrations that allows for, if you need like a simple use case, then you have the opinionated layer to use. If you have a more complex use case that it's quite exotic and unique, you don't need to start from scratch. You just use the low-level building blocks for your needs. I think that's a great trade-off for big organizations to have, and I recommend this design of low-level public APIs and higher-level integration that allows for easier integration with all kinds of use cases.
Okay, thank you. We still have a few minutes before we should leave the studio. So I will ask last question from the YouTube. How long have you been developing all of these Greyhound features?
Okay, so our previous Greyhound, which was based on the, let's say, Scala and Java concurrency primitives. So it has been in development for the last 5 years. And there are a lot of extra features that I haven't discussed today. So it really grown in size over the last few years and introduced a lot of use cases that are helpful for our developers. The rewrite is an effort that's been done for the last 6 months, I think, and using Zio, and we can see that the code that it took time, I don't know, like a month to write before without Zio, takes like a few days with Zio. So it's really increased the development velocity.
Okay, thank you very much. It was really great talk. I don't know what more to say. I will just inform now our participants that the next talk is in 7 minutes. And let me check notes. It will be From Zero to Deep Learning with Scala by Fabio Ticco. Yeah, in 7 minutes. So thank you very much.
Thank you, Les. Thank you, everyone.